On behalf of the Montana State University Honors College Honors Presents team, we thank you for watching Student Presents, an opportunity for students to share their interdisciplinary passions with others. Stay tuned for our next speaker, and if you are a Montana State University Honors student and are interested in giving a talk like this, please consult the description below. Enjoy!
Hello, my name is Matthew Thompson and I am majoring in chemical engineering. Today I will be presenting the hydrothermal carbonization of quantum dots from gelatin and orange juice. The results and procedures I will be discussing in depth were all performed in spring 2018 at Woodinville High School. Quantum dots have a uniform dispersed spherical structure centered around a semiconductor nanocrystalline core. Quantum dots behave like artificial atoms, roughly 2 to 10 nanometers in diameter, with fixed energy bands that either confine electrons or define electron holes. Absorbing energy, like from a UV flashlight, allows an electron to jump across that band gap, releasing a photon of light when the electron relaxes back down. The size of the dot alters the band gap behavior, changing the wavelength of light. Carbon quantum dots self-dope, meaning that their optical and electrical properties are tuned for blue photoluminescence, as they are around 2 to 3 nanometers. Doping describes how impurities and defects alter optoelectric properties. Using another compound, such as cadmium selenide, which is toxic, can result in quantum dots that are different sizes and emit other colors of light. Carbon quantum dots can be produced sustainably from biomass by hydrothermal carbonization, which converts organic compounds from food to other structured carbons under high temperature and pressure conditions. At temperatures between 180 and 200 degrees Celsius, and a pressure vessel, solid and liquid carbon sources can be converted into carbon quantum dots. What makes carbon quantum dots useful is the fact that they're non-toxic, so they can be used in a biological setting. They're stable and they're water soluble, so they can be put into aqueous suspension. The techniques used in industry are more refined than the DIY approach I took. An autoclave and hydrothermal synthesis reactor, like the one shown on the right, work well in industry with an appropriate carbon source and acid catalyst. Quantum dot applications include medical imaging, drug delivery, solar cells, and LED displays. An industrial setting optimizes for high yields and pure products, hence the additional filtration separation techniques. I improvised a pipe reactor from a galvanized pipe nipple and 2 end caps, wrapping the threads in Teflon tape to improve the seal. My acid catalyst was 12 molar HCl, and I used gelatin stirred in water as the solid carbon source. I loaded up the reactor and heated it in a chemical oven at 180 degrees Celsius for about 7 hours. Some safety points I would like to highlight. I wore gloves for handling the acid reactor and quantum dot solutions. There was a plastic bin of water next to the chemical oven if we needed to douse the reactor in an emergency, and the room was always occupied by myself or chemistry teachers who knew what the experiment was. Screw-on reactors are notorious for leaking, which you can see by the gelatin bubble that burst out from one of the ends. Even though the seal burst, quantum dots were still formed. Shining a UV flashlight caused the solid phase carbon quantum dots to glow blue, which you can see on the left and the right. The blackened crust is from burnt gelatin, but there are pockets of intact quantum dots still near some of the surfaces and around the bubble. For anyone who has autoclave biohazard waste, hydrothermal carbonization has the same exact organic burn smell as that. When I reran this with the liquid carbon source, I made some adjustments to the procedure to avoid some of the leaking problems. I tripled the Teflon tape layers and used a vise and wrench to make sure that nothing could leak out. Using orange juice, which contains citric acid, as a liquid carbon source, I repeated the same procedure. By the second run, the inside of the reactor was considerably corroded and was responsible for the dark particulate that you can see in the spill puddle and in the beaker and the inside of the pipe. I tried diluting some of the solutions, which made more concentrated test tubes darker in normal light, but this did not have a detectable impact on the luminosity of the quantum dots under UV, as you can see in the center image with the two different test tubes. I would like to note that because of unreacted orange juice, the solution was most likely tinged green by the quantum dots emitting blue light through that yellow-orangeous liquid. Although I could not eliminate the possibility that the orange juice produced slightly bigger quantum dots than the gelatin did, which would also explain the green photoluminescence. It has been reported in the literature that oxidation gradually causes quantum dot brightness to decrease over time, but quantum dots are also highly sensitive to pH. The pH of the environment modulates the surface charge of the semiconductor nanocrystal, its stability, and its solubility. And so I was anticipating that increasing the pH by pouring in NaOH to one of the petri dishes would cause the light intensity to decrease, and it would cause, if I poured in more acid, the light intensity to increase. Fortunately, the results that I saw did not back the increasing the acidity increases the brightness. It more or less was the same. But when I poured in the NaOH, there was some pretty good visual results. And so I'll show videos of what exactly is happening there. And the experiment videos tend to crash PowerPoint, so I'll pull them up manually. And this first one, we have the standard acidic petri dish in the front and the petri dish with NaOH added in the back. And you can see that there are marked differences between how bright and green the front petri dish is to the basic around pH of 10 in the background, and how much darker that is. And kind of a live time version of pouring in the NaOH. Afterwards, I poured NaOH into the standard petri dish, and you can see how everywhere that the base starts spreading out goes dark as it mixes in and goes into solution. And so gradually the green glow kind of goes away and it becomes much darker, like the one in the back. Here are the references that I used for some of the background. If you have questions or would like to see the in-depth procedures that I used for these experiments, feel free to contact the Honors College office and they can relay them to me. I have the in-depth step-by-step procedure and the amounts that I mixed for both the solid and the liquid quantum dot protocols. I also have a procedure for the exfoliation of graphene that is similarly DIY, and it can be done using cheap materials and public school lab equipment. These might be some good opportunities for those who are in Honors 210 and are mentoring a student with interests in nanotechnology or material science. Thank you for taking the time to tune in.